This talk is, yeah, so this talk will be given by Steve Nagler of Oak Ridge National Laboratory. It turns out I know Steve for many years. When I was still a postdoc, when I was so I checked his CV. It turns out he was a professor for many years at the University of Florida, and moved to Oak Ridge in 1995. Believe it or not, when I was still a postdoc at Oak Ridge. So he has since been staying at Oak Ridge and become a corporate fellow and very well known. And his work on the Kitaev lattice material has really, excited the field and started this huge amount of work on the alpha trichloride. Yeah. So okay. So Steve, it's all yours.
Well, thank you very much for inviting me to give this talk, and it's a pleasure to speak to this group. The title of my talk is Kitaev Materials and Magnetic Excitations in Alpha Ruthenium Trichloride. As I mentioned briefly before, Peng Cheng had asked me to make this a pedagogical talk, so I hope there are a lot of graduate students out there who might enjoy that. To the experts and colleagues who are working in a similar field, I will offer my apologies. This is going to be somewhat of a parochial talk when I finally get around to discussing results. I'm going to focus on those from our group. And another thing is any talk that's up to date at time t minus tau is out of date at time t plus tau. So, I've been a little generous in the tau, perhaps. So great, let's see. First thing that happened is now the slides are not advancing. There we go. So, of course, I'm at Oak Ridge National Laboratory, where we have a couple of neutron sources, and I'm going to talk later a fair bit about neutron scattering. And right now, I'm sort of sitting up in the corner of this building at the spallation neutron source, which you see here with a future target station that's now the beginnings of a project. And of course, we have the HIFER. So between these two sources, there are many neutron experiments being conducted, and I just heard that Tomo Umura was here recently. Now, I've been involved in many collaborations now on this material or related things. And so there are many collaborators I'd like to thank, but here I've only put those who were involved in neutron scattering papers that are already published. And I'd like to call out 4 of the young postdocs who've been heavily involved in this work over the past few years: Arnab Banerjee, Paige Lampin-Kelly, Christian Baltz, and Jana Samarakun. These are the people who are really sort of doing a lot of the hard work in the lab, and so I'd like to thank them in particular, along with my other colleagues. So here's what I will talk about during this time. I'll start with a brief overview of the model that actually inspired a lot of this kind of work, which was the honeycomb model by Alexei Kitaev. I'll just describe that. I won't go into it in great depth. And then I'm going to take a step back and talk about materials, beginning with single ion ground states in insulators, move on to how you might get the interactions that are characteristic of the Kitaev model in materials. And then I'll discuss a little bit about the magnetism of alpha ruthenium trichloride. I will take a brief digression about what we call fractional magnetic excitations, and then end up discussing inelastic neutron scattering and the possibility that there are these fractional excitations, in fact, in alpha ruthenium trichloride. So with that, let me move on to this. Before I start, here are some reviews of interest. Now, whether or not this material actually is at some level a quantum spin liquid, it's certainly motivated a lot of the work. So here are a few reviews of quantum spin liquids for students out there. And as far as what we mean by Kitaev material, which effectively is a material that has magnetic interactions similar to the Kitaev Hamiltonian, there are several articles that are out there about that topic as well, which I've also listed here. And you will find a lot of information there. So let me start with a discussion of the model itself. Okay, this model was published in 2006, 15 years ago, by Alexei Kitaev. His interest at the time was in quantum information and qubits, and he had devised something called the toric code, which I'm not going into. But he also came up with this exactly solvable model, which had magnetic anions, which turn out to be Majorana fermions as excitations, which could be the basis of a topologically protected qubit. So in fact, the motivation for this at some level was in quantum computing. And the model's very simple. Imagine that you have a honeycomb lattice where each spin, which is represented by a black or a white dot, has 3 neighbors. The reason I have a black and white dot here for the spins is it's actually a bipartite lattice, right? And I assume that I have an Ising type interaction, in other words, a uniaxial interaction with each of the nearest neighbors, but the uniaxial axis actually goes parallel to the bond. So that gives me 3 different Ising interactions along mutually incompatible bonds. And for spin 1/2, this model can be solved exactly. It's fully frustrated for either ferromagnetic or antiferromagnetic interactions. And the ground state is rigorously a quantum spin liquid, right? So this is the Kitaev model on a honeycomb lattice. And that's what actually inspired a lot of the work in the field. Now, the way he solved this was by converting more or less each spin into or spin operators into a set of Majorana fermion operators. I'm not going to run through any of the details of that, but I'll just say to understand what it looks like, first thing is one can define these flux operators that go effectively around a hexagon, and they form the following product, which you can see depends on the bond as defined here and the particular X, Y, or Z, which of course are not in the strictly 2-dimensional limit here orthogonal to each other. And this flux operator has eigenstates plus or minus 1. And the ground state is so-called flux-free, meaning that if I look at the system, the flux operator going around one of these hexagons always has the same value, okay? And if I flip a spin, this will produce 2 adjacent fluxes with a different value from the rest of the system. And those each behave as basically static Majorana fermions that don't move anywhere. The spin flip also produces a mobile Majorana fermion. So what's a Majorana fermion? It's a fermion that is its own antiparticle. So its creation and destruction operators are effectively linear combinations of a regular fermion creation and destruction operator. And basically the spectrum of the mobile Majorana fermion is Dirac-like. So if it's gapless, you'll have cones, etc. Okay. Now, depending on the relative ratios of the constant k sub gamma, which we'll call the Kitaev interaction constant, which can be in the X, Y, or Z direction, if these things are close together, then you have a gapless spectrum for the mobile Majorana fermion. And if one of them exceeds the sum of the others, you'll have a gapped spectrum. Okay, and this is in 0 field. You can also introduce a gap by a magnetic field. So it can be gapped by anisotropic interactions or by a magnetic field. So now here are some other features of this special quantum spin liquid. First of all, if I look at spin-spin correlations, the only ones that are non-vanishing are either the spin's correlation with itself or correlations with the nearest neighbor. Okay. Second fact, this fractionalization of spins into basically each spin can be considered as fractionalized into 3 fluxes and a mobile fermion. This results in a specific heat. If you had this system exactly, the magnetic specific heat would have 2 peaks as a function of temperature. The high temperature peak corresponding to the itinerant Majorana fermions and a low temperature peak corresponding to the localized Majorana fermions, each one of which carries an entropy of a half R ln 2. If I put in a magnetic field and sort of gap the bulk, which in this case, of course, is a two-dimensional surface, it turns out that I don't gap the Majorana fermion spectrum around the edges. And this gives me something that's, somewhat analogous to what you see in topological insulators. I have a half quantized thermal Hall conductivity in units of, here, this number Z is half odd integer, or in units of a half. So this is quantized in units of heat carried by half an electron. Now, the other thing is, it's an exactly solvable model, and it's also possible to calculate some response functions exactly for example, chi double prime of Q and omega that one measures in neutron scattering approximately, and some response functions for Raman scattering and so on. So here's an example of the imaginary part of the susceptibility calculated in a few different limits in this paper. And you can see here's in the gapless limit. What's kind of interesting is in the gapless limit, the response function at a given value of Q, this happens to be Q equals 0, shows a gap. That's because you create these static, if you like, massive gapped visons or gauge fluxes, and then a kind of continuum corresponding to the free Majorana fermion. And here's what it looked like if the Majorana fermion, the free Majorana fermion, has a gap in different limits. Okay, so these are just some basic facts about the model that inspired all of the activity I'm going to discuss going forward. So let me turn now to single ion ground states, just to give a little bit of background. And I apologize to the experts that this is going to be sort of very oversimplified, but let me think about transition metal ions initially in free space. And we have Hund's rules for finding their ground state terms, the values of L and S, which everybody who's studied solid state physics has probably seen in a textbook, which is, first of all, we would maximize S if we have many electrons in the ions, D levels, consistent with the Pauli exclusion principle. And we start by filling states with maximum values of the quantum number M sub L. And the ground state value of L is equal to the sum over these filled M sub Ls, which of course is the component of L along some direction. So we then have a ground state manifold with the degeneracy 2s plus 1 and 2l plus 1, where these are the total S and L for the ion. And we write the terms like this, just to remind you, 2s plus 1 times a symbol for L, which is SP, D, F, so on and so forth. So if I now consider the D series ions and I look at what happens if I put various ions in, right? For the D shell is empty, it's non-magnetic, and I'm assuming the other shells are totally filled. If I put in one electron, the total angular momentum is 2, according to Hund's rules, and these are the D levels that we normally think of. 2s plus 1, of course, is 2. If I have 2 electrons, I want you to note that actually in free space, the ion has an L equals 3. So that's an F state. Same with 3 electrons. With 4 electrons, we're back to a D state. Okay, and 5 electrons is actually half filled. And at this point in free space, we have an S state, right? So this turns out to be actually the important valence for the original conception of how you might get Kitaev interactions in a material. So we'll come back to that in some detail. So now I start filling up these levels, and I can now look at this as 6 electrons or 4 holes, D state, F state with 8 electrons, back to a D, and finally a non-magnetic shell. So these are actually sort of useful to keep in mind in order to figure out what's going on once we put these ions in a material. Now, the other thing to realize is that when we put an ion in a material, right, there will be some total ground state. It's not going to be exactly in any of the limits that I'm about to describe. It will be whatever the quantum mechanical ground state is. But these are ways of thinking about it that get us approximately correct in various situations. Okay, so the first thing is I'm going to take this ion, put it in a crystal. Now the environment is not spherical. And so in general, the degeneracy of this free ion term can be lifted. Okay, so when we have the field from the charge of the surrounding ions acting on the orbital angular momentum, if the crystal field isn't too strong, we have a perturbative approach where we use the L value determined from Hund's rules, and we figure out how that is perturbed by the crystal field. Okay, on the other hand, if the crystal field is very strong so that it overwhelms these Hund's rules, we apply it first to the orbital angular momentum of the individual electrons, and then we imagine filling electrons into those perturbed levels. So for one electron, the splitting is, of course, incredibly well known. So we'll look at this case first, one electron in an octahedral field. And famously, the fivefold degenerate orbital levels split into the T2G, triply degenerate, and the EG, doubly degenerate orbitals. So if you have a hole, by the way, they split, but in a reversed fashion. I think people know that. And if I switch from octahedral to tetrahedral local environment, that also flips these splittings for holes and electrons. So one of the points is if I have a threefold degenerate orbital state, right, by the Wigner-Eckhart theorem, the matrix elements in that state will be proportional to those of a similarly degenerate true angular momentum. So this behaves like an effective L equals 1, but with matrix elements that are proportional by some constant to the matrix elements of the regular orbital angular momentum L. So it can also happen, and typically does happen, by the way, that there are further perturbations from various sources that split these levels further. So very often one ends up with a singlet orbital ground state. In other words, quenched orbital angular momentum. But I'm going to go on to the cases of interest for us. So let's look at the 5 electron limit, the half-filled shell. Okay, in general, this free ion, as I mentioned before, is spin 5 halves, and orbital angular momentum 0. I guess there's a typo here. That should say S equals 5 halves instead of 1 half. Orbital angular momentum total 0. Now, if it's 0, the crystal field, which acts on the orbital angular momentum, has very little effect, right? And this is sort of typical for 5d electron systems in the iron series, like manganese 2+. But if I have basically larger ions, like say iridium 4+, right, where the electrons have a much bigger radius, there's a much larger perturbation from the charges from the surrounding ions, the crystal fields can overwhelm, right, Hund's rules. And then I imagine I have large splittings and I fill up these levels in accordance with Hund's rules. And what I find is with a T2G type triple orbital level and 5 electrons, I have a spin of 1/2. These guys cancel out. And because I can put that spin of 1/2 in any of these levels, I have effectively threefold degeneracy L equals 1. Right, so I'm left with spin 1/2, L effective equals 1. And you know, this S equals 5 halves we call the high spin state here, S equals 1/2 we call the low spin state. Obvious nomenclature. So, and I think further about this, right, if I have spin orbit coupling, this T2G level, which has given me an L equals 1 effective and an S equals 1/2, will split into manifolds of J. I prefer to think of this in the whole, if you like, picture. And I have a ground state that has an effective J of 1/2, doubly degenerate, okay? And it's a mixed spin orbital state. And as we'll see, a mixed spin orbital state is really what is needed in order to get anisotropic exchange interactions. Okay. Now, alpha ruthenium trichloride has ruthenium 3+. Roughly speaking, this sort of scenario holds, and there is a spin orbit level, right? So I show here actually a neutron scattering measurement of that spin orbit level, which can also be measured in other ways. It's not an easy measurement since you have to go to fairly large momentum in order to do it. And as Peng Chang and Jeff and others know, that makes it difficult to see the magnetic signal, but it can be seen, and it turns out to be about 200 millivolts. So that's roughly speaking thermal energies of a couple of thousand Kelvin. So if one is at temperatures low compared to that, then effectively each of these ruthenium 3+ behaves as a J effective equals a half system, or even if there are other perturbations, it's doubly degenerate and it's mixed spin orbital, which, as we'll see, can be good enough. So I also want to mention one other slightly more complicated system, which is 7 d electrons, exemplified by Cobalt 2+. Now this is an F state, which is orbitally degenerate, not 5-fold, but 7-fold. And if I put that in an octahedral field, I assure you it doesn't split into a 3 and a 2. It splits into a 3, 3, and a 1. And for this case of 7 electrons, that means the ground state manifold, if I don't have a super strong crystal field, is going to be L effective equals 1, S equals 3/2. There's also a possible low spin state, which has spin a half. But usually one ends up with this sort of weak or intermediate crystal field scenario. And if I think about what happens then, sort of typically in these Cobalt 2+ systems, you'll also have a departure from a perfectly cubic octahedron and some spin orbit coupling. Those tend to be of sort of the same, if you like, order of magnitude. And if I think of spin 3/2 L equals 1, that's a 12-fold degenerate lowest lying manifold. And under those, with this other perturbative Hamiltonian spin orbit coupling and some departure from cubicity looking like this, you end up with a set of 6 Promers doublets. Again, the lowest lying state is a doublet, and it has mixed L and S. So in fact, it turns out in this case, I can write these states as some linear combination in terms of ML and MS, if you like, L and S type eigenstates, and they will look like this. And if I simply assume that there's a true Heisenberg coupling between the true spins, but I project it into this mixed spin orbital doublet, it turns out that within that doublet, the effective, if you like, exchange interaction is anisotropic, right? So I can generate Ising-like or XY-like exchange in this way. And of course, I can also get additional terms in the Hamiltonian. So this is exemplified by this material, potassium cobalt trifluoride, seen here in some old literature. This is it behaves like a 3-dimensional Ising antiferromagnet. And it's not completely Ising, it's somewhat Ising, but you get a gapped spin wave spectrum, which you can interpret in terms of just a J equals a half model if I look at the lowest lying levels. But if I keep all 12 states in the lowest manifold and sort of diagonalize that problem, I see a whole set of levels that comes up, and these can be measured. In any case, this picture, it does give a sort of decent description of a lot of Cobalt 2+ systems in octahedral surroundings. So let me move from that brief revisitation of Hund's rules, etc., and talk about how we might get Kitaev type interactions. In other words, competing Ising-like interactions in materials. So this is really the paper that I would say started a lot of activity in the field. It was a realization by George de Kelly and Giniat Kaliulin that you could have Kitaev type interactions in materials under the following circumstance. So we think about this D5 system that I already mentioned in a low spin octahedral configuration. They were initially considering, strictly speaking, iridates. So we're in the strong crystal field limit. And one thing to note is that the largest perturbing energy in the system actually is the cubic crystal field. The next largest energy is strong spin orbit coupling, and that gives me a J equals a half ground state. And now comes the other ingredient that's important, edge sharing octahedra. And with that particular geometry, they could show that in fact you have anisotropic exchange, but the connectivity leads to some cancellations of what would normally be sort of J.J exchange here, so that what's left over is a Kitaev term that along each axis, well, I'll get back to the axes in a second, a Kitaev term that's different along 3 different axes, and a Heisenberg term. Now, without getting into the minutiae, let me point out that, of course, here we have octahedra that are 3-dimensional. It's not, strictly speaking, a 2-dimensional system, but you do have a 2-dimensional lattice of magnetic ions in one layer. But in fact, the X, Y, and Z axes now are mutually orthogonal axes that when I project them onto the hexagonal plane, do form the 120-degree lattice. But you know, the actual spin axes are orthonormal, and they do have competing interactions. So for all practical purposes, this maps onto a Kitaev type interaction with some extra stuff. Okay, now some considerations about the crystal structure. It doesn't have to be precisely a honeycomb lattice. If you have threefold connectivity, you can get the same thing even in some other kinds of structures, notably the hyper honeycomb structure. So it's really threefold connectivity with these edge sharing octahedra that's important. And by the way, there was a nice article published a few years ago that looked at more or less all of the different lattices that might satisfy that. And it's predicted also that some other kinds of structures, like the double perovskite structure, could have could satisfy the geometric requirements for this as well. So let me go back to what happens with this just Heisenberg-Kitaev model, which was conceived as applicable to honeycomb iridates like this sodium iridate. So I show here a phase diagram. J is the Heisenberg term, and that's going on the axis to the right. K is the strength of the Kitaev interaction going vertical. And what you see is the following. Okay, in this simple Hamiltonian, the ground states include all 4 of the possible collinear structures for a honeycomb lattice in 2 dimensions. So you see here, if J positive is antiferromagnetic in this case, and if that's dominant, you will get an antiferromagnetic lattice where the dark circles are spin up and the light circles are spin down. And again, this being a bipartite lattice, this is not frustrated in the conventional sense, right? If it's ferromagnetic dominant, you'll see a ferromagnetic lattice. And then depending on the ratio of ferromagnetic or of Kitaev to antiferromagnetic, I can get 2 other structures that are actually antiferromagnetic but different, the zigzag structure and the stripy structure. One way to think of these is in the pure antiferromagnet, all of the nearest neighbors are oriented opposite to a given spin. In the zigzag model, 2 out of the 3 are actually oriented the same. The ferromagnetic model, they're all the same. And in the stripy model, 1 out of the 3 are oriented the same. Okay, those are the collinear models, the collinear spin structures you can have on a honeycomb lattice. But you'll notice that actually this Kitaev ground state, the quantum spin liquid, survives in both the antiferromagnetic and the ferromagnetic limit. Now, one of the reasons that this survives is effectively there's a topological protection. So just breaking the symmetry of this by adding in some extra interactions does not destroy those spin liquid ground states necessarily, right? It depends on the ratio of the interactions. Now, this was realized fairly quickly is an oversimplification of reality. There are other allowed terms in the Hamiltonian. I'm not showing all of them here, but I'll show the leading one that people came up with, and one that's a little easier to picture, which is conventionally been called the gamma term. It's off-diagonal exchange. And if I go back to the other phase diagram I had, where sort of this is J, this is K, now here radially outward is gamma. And on the left is basically a classical phase diagram that was worked out by these groups, and on the right is a quantum phase diagram. And you can see that the zigzag and stripy ferromagnetic and antiferromagnetic ground states are still there, but you can also have the 120-degree ground state that's characteristic of sort of a Heisenberg antiferromagnet on a triangular lattice. You can have incommensurate spin ground states. And in the quantum limit, yes, the Kitaev quantum spin liquid ground state can survive with this Hamiltonian as well. And actually, here's a slightly newer phase diagram calculated, which indicates slightly different ranges there for the same Hamiltonian. But the point is, it's possible in principle to have this quantum spin liquid ground state, even if the Hamiltonian isn't exactly a Kitaev Hamiltonian. And I should point out, it's also been proposed that there are other kinds of spin liquids. For example, if I just had this gamma term, I can get a gamma spin liquid. So there are quantum spin liquids that in principle might exist in materials that have Hamiltonians like this. So here are examples of these 5D electron-based Kitaev materials that have been investigated. Now, in this case, by Kitaev material, what I mean is that at least part of the spin Hamiltonian arguably contains these mutually incompatible, conflicting, competing Ising-like interactions. And if we want to say these systems are frustrated, we realize they're frustrated by competing interactions. So you can see there's a whole mess of iridates in here, some of which are honeycomb, some of which are hyperhoneycomb, and there's alpha ruthenium trichloride. Now, every single one of these orders in some fashion, at least in zero field, at a low enough temperature. A lot of them tend to order in the zigzag phase. Some, well, every single one except one that I'll mention. Others are antiferromagnetic, etc. The one outlier here is this protonated lithium iridate, which it says here spin liquid, but this has a complication that there's disorder in the system, which actually can have a significant effect. Anyway, I'm going to now specialize shortly to alpha ruthenium trichloride. Before I do, I'd like to mention that there are, as I said before, other systems. Gideon Kalyulin wrote a paper with a colleague pointing out that Cobalt 2+ systems can lead to a similar thing, in other words, D7 transition metals. And there's a nice summary by Matome and collaborators in this paper that suggests a lot of other materials that might have these Kitaev interactions present. So a lot of these are D7, Cobalt 2+, some of them are F electron systems. Again, I'm not really going to go into that in any detail. So let me now turn specifically to alpha ruthenium trichloride. So this is a material that's been studied for a very long time. And I draw your attention here, a couple of papers from 1963 and 1967, where people looked at its structure and they looked at the magnetism. And the alpha ruthenium trichloride indeed has a honeycomb lattice. It has ruthenium 3+, which is D5, in an octahedral surrounding in the low spin configuration. So it meets all of the criteria for a system to have Kitaev interactions that I mentioned before. The actual at low, well, let me come back to the crystal structure in a second. I'll just say it's, this is a very two-dimensional material where the layers are just held together by van der Waals interactions. And that being the case, you can get, in principle, a lot of stable structures, kind of like a clay, different stackings and so on. And, you know, it was recognized very early that there's a tendency for these things to form stacking faults. And if you look in the literature, you'll see all kinds of, in fact, slightly different refinements of the crystal structure. So that's been an issue with this material for a long time. It's very easy to slide one plane over the other without doing much except changing the stacking sequence. The stacking sequence at low temperature seems to be threefold. but exactly what the structure is turns out to be tricky and can vary from sample to sample. Now, Ping Cheng asked me how we came to study this. And I will tell you, it was very simple. We were aware that the iridates were very interesting based on the considerations people have mentioned before. If you go back and look at the literature at that time, it's very common to see statements like, well, the important thing is it has to have strong spin-orbit coupling. And as I mentioned, actually, the strongest interaction really is the cubic crystal field in this Cayley-Yulin scenario. The next strongest is spin-orbit coupling. Iridium 4+ was the obvious candidate. The materials existed, but we were interested in looking at the excitations. And as those of you who are experts in neutron scattering know, iridium materials are rather challenging. So in our case, I found this by trying to look for a material specifically with this structure with ruthenium 3+, which I found in Landau-Bornstein, and we started working on it. And apparently at the same time, the group at University of Toronto was also thinking along the same lines. But I will say, we certainly thought of this without knowing anything about that. When we got a hold of some of the material with the intent to make single crystals, we found that what we had was basically a very small amount of ruthenium trichloride and a lot of other stuff, even though it was sold as 2,9s pure or whatever. Now, the reason for that was this material that was studied a long time ago was used as a catalyst. And if you have a material used as a catalyst, it doesn't have to be terribly pure. So at that point, this is already, I think, 2013 or even 2012, when we first started trying to do this, we just bought this junk. And, my colleagues like David Mandris are very particular about not trying to grow crystals out of junk. So we invested a long time taking the junk and purifying it till it was 3,9s alpha ruthenium trichloride, and then we grew crystals. It was probably too conservative on our part in one sense. The Toronto group went ahead and just used the stuff that you bought, and by vapor transport got some crystals that were sort of the right phase. But we were able to get some really big ones that helped us with our inelastic studies. So we messed around for a couple of years doing that before we really got the samples we wanted. So that was quite a long time. In any case, once we had them, and again, I apologize for only showing Oak Ridge data on this, but we only have an hour. What you find is that this stuff orders antiferromagnetically in a zigzag phase at low temperatures. So here you see a couple of pictures of different samples. For what I'll call a pristine sample, you see a single transition around 7 Kelvin. Here you see it in really, that's the susceptibility. Here you see it in the specific heat. And here's a measurement of a neutron scattering peak. Okay, and indeed, this does correspond to the zigzag phase. And it corresponds to the zigzag phase with a 3-layer periodicity repeat in the magnetic structure. Now, you'll notice that this is a very sharp specific heat peak, relatively speaking. If I handle the crystal and I remeasure the specific heat, I find this is broader and I start to see some other structure. And in fact, our colleague J.Q. Yen deliberately took and sort of did some mechanical work on some of these crystals. And what he found that as you work it, you lower this amount of specific heat at 7 Kelvin and you start to see some response at other temperatures, most notably 14 Kelvin. And as you keep deforming it, instead of a sharp transition at 7 Kelvin, you get a broad one at 14 Kelvin. And of course, if you have a powder, you just get a really broad transition at 14 Kelvin. So what's going on here? Well, basically you're putting in stacking faults. The system with stacking faults changes things a little bit. Luckily, most of the most interesting physics is two-dimensional, so it's not necessarily affected by this, but one has to realize that there are significant, the magnetic structure is actually a 3-dimensional magnetic system with a 3-dimensional ordered structure, and it is affected by these stacking faults. And in fact, the earliest crystals that we made had some amount of material with stacking faults in it, and they generally showed both transitions. If you looked at the 7 Kelvin transition, it was pretty sharp, and it occurred at wave vectors with L equals 1. The 14 Kelvin transition was broader, occurred at wave vectors with L equals 3/2. So basically, this one, the green one, the 7 Kelvin transition, is zigzag with a 3-layer periodicity. The 14 Kelvin transition is zigzag with a 2-layer periodicity. So what's the reason for this? Well, at the lowest temperatures, the crystals have at least a pseudo 3-layer crystal periodicity that kind of imposes a boundary condition. And that it turns out that this thing basically wants to have layers that are antiferromagnetically coupled to each other. But if there's a periodicity of 3, that's kind of frustrated. So that actually lowers the transition temperature a bit. If I put in some defects by sliding some layers around, that actually relieves the antiferromagnetic frustration going perpendicular to the layer, and I get a higher transition temperature, but a broader temperature, or broader transition rather. One thing that's kind of interesting is if I compare the specific heats of the ruthenium trichloride to any of these iridates, you can see how much sharper it is, right? Nobody saw sharp transitions in these iridates, and you might suspect that maybe these have quenched in stacking faults or something as well that kind of broaden those transitions. But I'll just point out, when you make a pristine crystal of this stuff and it has very few stacking faults, you see a very sharp transition. Now, if one applies a field in the plane to this, it's a fairly modest field, will actually kill this magnetic order. And it turns out that the most sensitive direction to put a field is perpendicular to a bond connecting one ruthenium to the other. And if you do that, something like 7.3 or 7.5 Tesla, the magnetic order will go away, okay? And after this was discovered, and Jeff Lynn was involved in some nice work looking at this as well at NIST, it was hypothesized that actually this resulted really in a field-induced quantum spin liquid state, right? So interesting to look at this thing potentially in a field. So there's one other thing before I start talking about neutron scattering that's interesting to note. You will maybe remember that I mentioned that for a pure Kitaev model, the specific heat actually has 2 peaks as a function of temperature. The highest temperature corresponding to the mobile Majorana fermions, and the low temperature peak to basically the visons. Well, here are some measurements originally of a zero field crystal that did show this broad peak you might expect from the mobile Majorana fermions up at 100 Kelvin, sort of 15 times where the transition temperature is. And that was done by the Korean group. A German group with Leudel et al. Measured the specific heat fairly carefully, and they did it now in a field of 9 Tesla, which is enough to kill the order. And very interestingly, they see this double hump feature, which if you believe that this thing could be related to a Kitaev quantum spin liquid, might be the signature of, on the one hand, the visons or static fluxes, and the other hand, the Majorana fermions. In any case, it turns out to look that way, and that also has whetted people's appetites for thinking maybe you have Majoranas here with some thermodynamic evidence for them. Well, let me now talk about fractional excitations in quasi-1D magnets as just an introduction to what we might want to see or in neutron scattering if I have a fractional excitation. So let me first of all say what I mean in this case by a fractional magnetic excitation. Inelastic neutron scattering measures matrix elements between one state and another. So if I'm at 0 temperature, that would be between a ground state and an excited state. And the non-vanishing matrix elements generally have a change in either S or L, a plus or minus 1 or 0, right? Those are the states that contribute to the response function that's measured in inelastic neutron scattering. So if I have a simple situation with an ordered ground state, and I think of what makes a regular magnon, which is a spin flip, a delta S equals plus or minus 1 type matrix element, I'll get one excitation, and conservation rules mean that there'll be a fixed momentum and energy relative to the ground state. So I tend to get something that looks like this. I get a sharp peak as a function of Q, and I have a sort of well-defined dispersion relation. Now, what I mean by a fractional excitation is something where the intrinsic excitation does not have a spin of 1 or 0 relative to the ground state. So if I measure a matrix element with delta S equals 1 or delta S equals 0, if let's say the excitations are spin-ons that have a spin of a half relative to the ground state, I will be sampling a state that has multiple excitations. So the conservation laws are satisfied if I have many combinations, if you like, of these elementary excitations. And this gives me, for each wave vector, it'll give me a broad continuum of scattering. And the examples that I've plotted here happen to be germane for the antiferromagnetic Heisenberg chain, for which it's known that the ground state is a singlet. It turns out that the natural excitations are spin-ons that have a spin of 1/2 relative to the ground state, unlike sort of regular magnons or spin waves, which have a spin of 1 relative to the ground state. And the spin-ons effectively in the neutron scattering experiment are created only in pairs or even numbers. So the physically observed states have a total spin of 1. And actually, of course, most people will be familiar with this as one of the problems that got a lot of fame for Duncan Haldane, who showed that there's a topological term, if I look at this from the point of view of field theory, so that if I have an integer spin at each site in the original Hamiltonian, these spin-ons are bound together, and I get a sharp mode with a Haldane gap. If I have, on the other hand, half-odd integer spin, the spin-ons are free in a sense, and then S of Q and omega has a continuum, as I showed on the previous slide, which is a signature, if you like, of fractionalization. And in fact, this has been seen, both the Haldane gap and the free spin-ons in many different systems. I'm giving here as an example this potassium copper trifluoride. Now, in fact, I would argue this is a quasi one-dimensional spin and a half Heisenberg antiferromagnet. And it's probably the first one, well, on 2 accounts. It was one of the first experiments that got something really useful using time of flight inelastic scattering on a single crystal that was anisotropic. And it was also, I would argue, the first clear proof that you really had these spin-ons that gave you a response above any renormalized spin wave, although there had been hints before that of asymmetric line shapes and so on. It actually clearly showed the spectrum. This is how it was measured in the 1990s. And here's how such a thing is measured closer to today. So you can see we can just do a neutron scattering experiment. And here we plot momentum on the horizontal, energy on the vertical, and intensity by color. And one can do sort of beta ansatz type calculations to get what the spectrum is, and you compare that to experiments, and it's very close, right? So we see these things. But there's a bit of a complication, which is KCUF3 is actually a 3-dimensional material where it has very strong interactions along the chains, but weak interactions between the chains. And for this Heisenberg antiferromagnetic chain, any amount of coupling between the chains will lead to an ordered state. So I can make a little phase diagram that looks like this, right? Here's the coupling between the chains, here's the temperature. If I have absolutely no coupling, I do have this state that only supports spin-ons, which, by the way, some people would call a type of quantum spin liquid. But otherwise, I actually have some magnetically ordered state. And so the question is, if I have a pure chain, the intrinsic excitations are these fractional excitations. What happens if I don't have just a pure chain, but if I have coupled chains so that the system orders? And what we see is the following. If you're above the Néel temperature, which turns out to be 40 Kelvin for KCuF3, you see something that just looks exactly like the one-dimensional solution for non-zero temperature. If I'm below that temperature, if I look at very low energies that are characteristic of the interchain coupling, I actually do see sharp spin waves. And at a slightly higher energy, I will see something that's basically a longitudinal fluctuation, unlike the spin waves that are transverse fluctuations. These days, we would call that the Higgs mode. And at higher energies, I still see signs of this continuum of excitations coming from the fractional excitations. But the point is this: if you're at low temperature and the system is actually ordered, you will see quite possibly a coexistence of sharp modes and broad modes. Okay, why do I mention that? Well, as you'll see, we see something similar to that in inelastic neutron scattering on alpha ruthenium trichloride. So let me now take a look at that. So here we have a quasi 2D antiferromagnetic system, and I'm just putting up a plot here of a regular spin 1/2 antiferromagnet in 2 dimensions, just to give some idea what you sort of expect to see from, if you like, ordinary magnons. So if I was to measure these with a triple axis, I would measure an energy for various different values of Q, and I could plot a dispersion relation like this that shows the energy as a function of momentum. And if I think about rotating this about the vertical axis, I can see that, roughly speaking, I have sort of a conical dispersion. That happens to be a square lattice, but if I look over here at slices of constant energy now over the 2-dimensional surface, I'll see around each one of these antiferromagnetic points, I see a circle with a radius that increases as the energy increases. These are just cones of dispersion. And eventually, when I'm close to the zone boundary, I sort of see the outline of the zone boundary. That's what spin waves sort of look like conventionally if I do a constant E plane, which is what we do a lot of times with the time of flight in elastic data. So let me consider what these will look like for a zigzag state. Now, in fact, it depends on the details of the Hamiltonian. Various different Hamiltonians can lead to zigzag states, so I'm just picking one. What will happen here is that I will have dispersion that comes down to 0 at something equivalent to an ordering wave vector, or M point, in this 2-dimensional model. And typically I will have equally populated domains. So I will see something with a 6-fold symmetry, and each one of these points is effectively a spin wave cone around an ordering wave vector. Okay, so that's sort of typical of what happens. The details of what happens everywhere in the zone depend on the details of the Hamiltonian. For the Heisenberg-Kitaev model, these gamma points are sort of basically sort of flat modes that are sharp in energy, just in spin waves. Now, if I look at alpha ruthenium trichloride and I do a measurement like this, here's what I see. I do see these spin wave cones at low temperature. I also see this other piece of scattering at low energies centered around the gamma point, right? Which we didn't necessarily expect from ordinary spin waves. And if I look at this more closely, now I'm plotting one direction in reciprocal space here and energy vertical. And you can sort of see the shape around what's a 2-dimensional gamma point. Now, I should point out, in order to do this, we have to sum over some non-zero range of momentum perpendicular to the A star B star plane here, if you like. So we're looking at something that we're sort of assuming is quasi 2-dimensional, which turns out to be a pretty valid assumption. And then if I look at low energies, I see this thing here with sort of these well-defined cones and a piece in the middle. And at higher energies, I see this kind of, if you like, Star of David shaped scattering. Okay, and there's a broad continuum at the gamma point. And if I do this as a function of one of energy, and I look at the intensity at one momentum, which corresponds to the gamma point, what I see is at low temperatures, I see a sort of broad piece with some sharp peaks. And here's the similar plot to what I showed before, HOO and energy. This is measured in a slightly different way. But you see these are the sort of sharp peaks, and here's the continuum part. If I raise the temperature above 7 Kelvin, the sharp peaks go away and I'm left with the continuum. So you can see that here in a constant Q scan and here in one of these sort of energy momentum scans. So here's something showing more broadly the Q and temperature dependence of the scattering, showing this kind of large continuum. And what I sort of maintain is that, you know, we have something similar in spirit to what you see in the quasi 1D chains, which is when it's ordered, you see spin waves plus some continuum that could be coming from fractional excitations. And when it's disordered, you see only the fractional excitations. So what about this applied field that kills the order? Well, here's what I see at 2K and 0 Tesla. And again, here's 15K and 0 Tesla. If I put on a small field, actually, the spin waves that I measure get stronger. This is because of a domain repopulation effect and how the neutron scattering cross-section works. But as soon as I go beyond the critical field where it disorders, the spin waves die and this continuum is present very strongly. So it looks a little different from this, but it seems that in this disordered state, whatever this disordered state is, we see only the continuum scattering. All right, so are those evidence of fractional excitations or Majorana fermions? Well, one piece of evidence that I will say is still highly controversial is a claim that if you look at the thermal Hall effect, when I get in the right situation above the disordering field, between that field and another field, I actually see a thermal Hall effect that's quantized at the value sort of originally predicted by Kitaev. At least that is the claim in this Nature paper of Kasahara et al., now published in 2018. They come up with a sort of following phase diagram that there's antiferromagnetic order. They have this plateau here, which they think could be the Kitaev spin liquid, and then another transition to some what they call a non-topological phase. Do we see that? Well, here's a measurement that goes higher in neutron scattering. This is a triple axis measurement done at Flex, for those who are familiar with it in Germany. And now we're looking at two different gamma points in 2 dimensions, but different wave vectors in 3 dimensions, right? And again, this is at low temperature in the ordered state. It is a 3-dimensional system. What you see at 0 field are, there's a couple of sharp spin wave peaks, and here we do see a continuum. And when you go into what we think is a disordered phase, these sharp peaks are very hard to see or invisible with neutron scattering. The continuum is stronger. And eventually we get to a state where we have sharp peaks at a lower threshold and a fairly strong continuum above that. Okay, here's the sort of dispersion measured at 13.5 Tesla and 0 Tesla along the L direction. And here's sort of the energies. And in this region here, we're unable to detect what you would call magnon peaks. So this, combined with some magnetocaloric effect, caused us to construct this phase diagram. There's a second ordered state that I haven't described here, and I won't unless somebody's interested. But above this, we see something that's disordered that might be a quantum spin liquid. That's maybe, this is sort of like the Matsuda quantized thermal Hall effect. And then something else happens up here, which we think the system's at least partially field polarized. So what really is going on here? Well, a lot of conflicting information and different ideas that people have, but I think it's still very possible that you have a quantum spin liquid in some intermediate regime here. Here's the phase diagram we produced compared to the one that Matsuda published originally. So I'm getting now to sort of the end of my presentation, and then we'll look at some questions. So here's some remarks and open questions about where this field's at. First of all, there are some dissenting views about the excitations. So some people would argue that there's actually no Kitaev term in the Hamiltonian, and it's in no way related to a spin liquid. The broad scattering is from decayed magnons. And I think that argument is presented well in this paper by Maximov and Chernyshev. So I encourage you to look at that. I actually don't agree with that, but they have some interesting points. Are those quantized thermal Hall measurements valid or not? Again, there's disagreement. Many groups have not been able to reproduce it. There are a couple of groups who say they have some evidence in favor of it, but it's a little bit different. I would say some of the spectroscopic measurements, and I haven't gone into this, either give conflicting results or results that can be interpreted as conflicting. I would say that, terahertz measurements have been interpreted as saying there's a sharp mode for all fields. Neutron scattering doesn't see it. Some of that difference could be the difference, if you like, in energy resolution, but based on other measurements, I don't think it's completely that. I think these experiments are perhaps sampling some different things. There are obviously possible materials issues with this. When you handle it, you can put in stacking faults. There may be stoichiometry issues. Those may turn out to be very important in the details of things like the quantum thermal Hall measurements. And I've mentioned this before, but I'll also say there are new systems being put forward with similar characteristics. Quite a few papers recently on the Cobalt 2+ materials, but there are others. So I think I've taken up my time. Here's some of our group's neutron scattering references on ruthenium trichloride. And of course, there are other groups from Toronto that's been working at NIST and also the Korean group and various others. But like I said, this is a bit of a parochial talk. So the figures I've taken have largely come out of these papers. So thank you very much for your attention, and I'll be happy to take any questions.
Thank you, Steve, for such a nice talk. I mean, it's very pathological and really summarized the field well. Yeah, thank you so much. Yeah, so do I have some question? Please raise your hand. Anybody? There was some question by Chandra.
Yes.
Okay, Chandra, you want to go ahead? Ask in person.
Well, if I look,
no, I don't.
Okay, I don't disagree with what.
I don't have anything substantive to ask. Just a matter of. At one point, you were implying that one could interpret you to be implying that one can never measure S equal to half excitation directly. I think it's not possible. You always measure with neutron.
Yes, I agree, and I'm sorry if it didn't seem like I made that clear, because I think I did say that.
So it always requires a theory. It always requires a theory in between to come to any conclusion about the spin half excitations.
Okay. Yeah.
Yes, but I will point out some things, however, that are that are characteristic that I didn't mention. Obviously, you can have continua from two regular excitations, right, with delta S equals 1 and so on. But if that's coming from a multi-magnon spectrum, you expect that anything that renormalizes the one magnon spectrum will also renormalize the multi-magnon spectrum. Whereas for these sort of quantum fluctuation spectra, which I'll agree, we have to interpret indirectly. That renormalization is generally lacking there.
So. Yeah, I mean, in cases where the theory is absolutely clear, like one dimension, there is absolutely no issue. But in cases which are complicated and the issue of the experimental sample reproducing the model is in doubt, that was it would be nice if one had some more very direct and specific characters, aspects of experiment, so that one could say that they are unusual excitation, which I'm sure in models there are. But in materials there are. It remains to be decided.
Yeah, thank you, Chandra. Yeah, Tara.
Thank you. Yeah, I had a question about can one, so based on the neutron scattering data for excitation perpendicular to these frustrated planes, can one, is it now clear that it cannot be a three-dimensional spin liquid, or I mean, if at all, I mean, we don't even know it's a spin liquid in true sense, but yeah, can one rule out that scenario that there is some, could it be like a fractional excitation in the perpendicular direction because of your data, the 00L, or I mean, that was too fast for me, so I couldn't tell.
Okay, so what I can say is in the limit where we have sharp, well-defined excitations, like the magnons at zero field in low temperature, or in the high field limit where it's partially polarized. You know, what we measured there were well-defined excitations. All we basically show for certain is that there is a certain amount of magnetic coupling between one layer and the other, which is not surprising. I mean, after all, it is a three-dimensional magnetic system. Without knowing what the Hamiltonian is, which I would argue we still don't really know the magnetic Hamiltonian in the system definitively, you can't tell from that precisely, you know, how large that, say, JC is, or whatever it is, compared to the other interactions. We can estimate it based on reasonable arguments as it's relatively small, like a few percent, but we don't know. Now, could there be some sort of three-dimensional quantum spin liquid? Well, sure, but I don't think we've shown that in any sense, that it has to be three-dimensional. I think the most likely scenario is that we have something, you know, the system is close to some kind of quantum spin liquid that is basically fundamentally a quasi 2D quantum spin liquid. Same way KCO3 is a three-dimensional material, but you know, it's very close to the 1D Heisenberg eddy for magnetic chain and shows its excitations. That's what I believe.
The reason I was asking about this three-dimension, and I wanted to get maybe some, if you have any comments on this experiment by Von Ong's group on when they apply in-plane magnetic field, even then they see oscillation. So if it were, I mean, this is just imagination. I mean, I don't know whether what I'm saying makes sense, but if it were a three-dimensional some system, then you can have orbital effect even and you apply in plane, because
right. And they of course they have, if I recall correctly, some relatively exotic explanation for it, right? That it's still quasi 2D, but you know, I don't claim to know what the right solution to that is, right? I mean, my instinct is this is a quasi two-dimensional magnetic system, you know, but it's not fully two-dimensional for sure.
Right. Okay. So let's get Han Yu to ask a question. Han Yu?
Oh, yes, I'm here. Thanks very much for the very nice talk. I have a quick question regarding the detection of a spin-on continuum. So, of course, neutron always has this elastic band that limits what type of a gap can be resolved.
Sure.
If that is not a concern, say, by using terahertz, what will be the desirable minimum resolution that is needed to actually clarify that there's a spin-on continuum instead of a bound spin-on?
Well, okay, I mean, the terahertz, I will say, yes, it has better energy resolution than you can generally hope to get with neutron scattering. On the other hand, with neutron scattering, we know exactly what matrix element we're measuring. And a lot of the experiments that are done at fixed frequency, you know, and then you vary the field, right? That presents another challenge because you can't measure any frequency lower than this fixed frequency, right? So if I look at some of that data, you know, I'm not sure that you can completely interpret it as gapped all the way through. Now, in terms of your question, how far down do we have to measure before we're convinced that there's a continuum with no bound state at the bottom? Well, I guess, you know, you have to make another decision, which is, you know, what's the minimum amount of, if you like, spectral weight that would be in that bound state. right? I don't know the answer to that. What I know is that in this and in other neutron scattering experiments we've done, there's always a region where we can't detect anything that looks like there's a lower peak, and that seems to happen rather suddenly, right? In the terahertz experiments, they believe they see a peak that goes all the way through. So I'm not sure what the origin of that is. I think that if we accept other estimates of what might be the energy of a presumed Vison, which I have to say I consider this totally speculative, right? We really don't know. We'd have to go down to some number of tens of microvolts probably to be completely sure, right? But I think the answer is nobody really knows at this point. I mean, the program we're on now is, we have more data at high fields that has to go out in the other directions, right? In order to try to get a better handle on what might be the correct spin Hamiltonian, if you like. What we'd really like to do is measure in 100 Tesla. Unfortunately, we don't have that ability.
So Steve, I was curious on several things. I mean, so in your measurement that you said earlier that when you put some sort of deformation, you can actually destroy this very sharp peak. I mean, first of all, is this transition first order, the 7K transition that you see, or second order?
It might be weakly first order.
Okay, so then what sort of deformation you do that can actually destroy such an order? I mean, what happened to your spin excitation spectra? Is there any controlled way of probing these?
I'm sure there's a controlled way. I'm not sure exactly how to do that. I mean, I suppose you could set this up and you could actually have controlled amounts of pressure or shear or whatever, but it's basically this, Pengsheng, imagine without getting into exactly what the quote unquote right crystal structure is for this, it's a 3-layer periodicity. And if I am imagining I have a honeycomb lattice, right? I'm putting these up in a staggered fashion, where if I project down, I will see a triangle of magnetic ions, right? But I can take any one of those layers and slide it along and put it in the wrong position so it doesn't go 1, 2, 3, 1, 2, 3. It gets interrupted somewhere. And the point is that the interlayer coupling being antiferromagnetic, it's frustrated by this 3-layer periodicity, right? So if I break that up, it allows it to go completely antiferromagnetic. Right, and so putting in a defect like a stacking fault lets it do that. But in practice, right, these things being sort of like clays, you could get a lot of different ordering structures with different periodicities that could have slightly different magnetic structures with different transition temperatures. Those ones seem to be the most prominent.
But does that affect your continuum?
No, I mean, that continuum that we see appears to be quasi 2-dimensional. So I would say no, in at least at the level that we are able to measure it. Now, of course, in order to see it in these time of flight measurements, right, we actually need to, well, I'm going to back off on the no in a second because I'll talk about this, the measurements with the triple axis in a second. But in the time of flight measurements, you have to integrate, as you know, over some non-zero momentum thickness perpendicular to the plane. So you're always doing that. If the fact that this thing actually has, at least when you have spin waves or magnons, it has some dispersion in 3 dimensions. If I look at it, right, in the high field limit, you'll see that there's a lower bound above which there's a continuum, and that lower bound does depend on the value of L. So in that sense, it definitely affects the lower bound of the continuum when you're either in the magnetically ordered state or the partially polarized state. If there's truly a disordered state there, does it impact it there? Well, not as far as we can tell, but that might be in detail some open question there.
So have you completely solved just the spin wave Hamiltonian?
No.
Just a spin wave Hamiltonian. Yeah, I just see you the spin wave spectra, but I mean, you haven't fitted even with a Heisenberg type of model?
Well, the problem is it's frustrated, and you can come up with more than one Hamiltonian that might fit it, right?
I see.
So, I mean, the way that you would like to resolve it is you, and of course, you know, people would argue that, well, the magnons actually decay for various reasons. And so that kind of makes it hard to get, it's not like it just has a dispersion relation and nothing else. So the way you'd like to solve it is fully polarize the system so it's in a ferromagnetic state. And then that can resolve a lot of the ambiguity. So we've gotten as far as partially polarizing the system, and we do have some time of flight measurements in the other directions, and we're still analyzing them. I will say, I don't think that any of the published Hamiltonians actually completely explain the data.
Okay.
So,
Okay, well, that's I mean, so okay, so I mean that's good, right? That means you have, you know, more things to do, more measurement to do.
I have a feeling there's still a lot more to do on this and related systems.
Okay, thank you very much. Any other question? Yeah, if not, yeah, let's really thank Steve again for this stimulating talk. Thank you so much, Steve.
So I'm waiting for Jeff to say that he's got it solved.
No, not at all.
No, I mean, the problem with Jeff is that he doesn't have a reactor, right?
Yeah, that's a problem.
Well, we all hope that that situation will be solved as soon as possible.
Yeah,
And
2022. The not before date now is April 2022.
yeah, so I've heard.
Yeah.
Well, hopefully we get NIST running and we get our facility upgraded and running, and there'll be plenty of neutrons to go around. But
Never.